We have just completed the foundation, and now we will dive into the device. In this module, you will learn about reset, interrupts, and system initialization. There are various reset sources available for this device: an external reset pin, watchdog timer reset, power on reset, which generates a device reset during power-up conditions, brownout reset, which generates a device reset if the power supply drops below specifications for the device, as well as a missing clock detect reset. Additionally, the device incorporates an on-chip voltage regulator to generate the core voltage. After reset, the object mode and address mode bits are set to 00, placing the device in test mode. The PI block's disabled, and the global interrupt line is disabled. The reset vector is fetched from the boot ROM, and the bootloader sets the object mode and address mode bits to C28X mode. Then we determine if the emulator is connected by checking the JTAG test reset line. If the emulator is connected, we are in emulation boot mode. The boot is determined by two RAM locations named EMU_key and EMU_B mode, which are located in the PI block. If the emulator is not connected, we are in standalone boot mode, and the boot is determined by two GPIO pins and two OTP locations named OTP_key and OTP_B mode, which are located in the OTP. In emulation boot mode, first the EMU_key register is checked to see if it has a hex value of 55AA. If either EMU_key or EMU_B mode are invalid, the wait boot mode is used. These values can then be modified using the debugger and a reset issued to restart the boot process. This can be considered the default on power-up. At this point, you would like the device to wait until given a boot mode. If EMU_key register has a hex value of 55AA, then the hex value in the EMU_B mode register determines the boot mode. The boot modes are Parallel I/O, SCI, SPI, I2C, OTP, CAN, M0 SARAM, Flash, and Wait. In addition, there's a Get mode, which emulates the standalone boot mode. In standalone boot mode, GPIO pins 37 and 34 determine if the boot mode is Parallel I/O, SCI, or Wait. The default unconnected pins would set the boot mode to Get mode. In Get mode, first, the OTP_key register is checked to see if it has a hex value of 005A. An unprogrammed OTP is set to the flash boot mode as expected. If the OTP_key register has a hex value of 005A, then the hex value in the OTP_B mode register determines the boot mode. The boot modes are SCI, SPI, I2C, OTP, CAN, and Flash. In summary, the reset code flow is as follows. The reset vector is fetched from the boot ROM. Then, the execution entry is determined by emulation boot mode or standalone boot mode. The boot mode options are M0 SARAM, OTP, Flash, and bootloading routines. The internal interrupt sources include the general purpose timers 0, 1, and 2, and all of the peripherals on the device. External interrupt sources include the three external interrupt lines, the trip zones, and the external reset pin. The core has 14 interrupt lines. As you can see, the number of interrupt sources exceed the number of interrupt lines on the core. The PI, or Peripheral Interrupt Expansion block, is connected to the core interrupt lines 1 through 12. This block manages and expands the 12 core interrupt lines, allowing up to 96 possible interrupt sources. I will explain the interrupt processing flow from the core back out to the interrupt sources. The INTM is the master interrupt switch. This switch must be closed for any interrupts to propagate into the core. The next layer out is the interrupt enable register. The appropriate interrupt line switch must be closed to allow an interrupt through. The interrupt flag register gets set when an interrupt occurs. Once the core starts processing an interrupt, the INTM switch opens to avoid nested interrupts. The core interrupt registers consists of the interrupt flag register, interrupt enable register, and interrupt global mask bit. Notice that the interrupt global mask bit is 0 when enabled and 1 when disabled. The interrupt enable register is managed by ORing and ANDing mask values. The interrupt global mask bit is managed using inline assembly. We have already discussed the interrupt process in the core. Now we need to look at the peripheral interrupt expansion block. This block is connected to the core interrupt lines 1 through 12. The Pi block consists of 12 groups. Within each group, there are 8 interrupt sources. Each group has a Pi interrupt enable register and a Pi interrupt flag register. As you can see, the interrupts are numbered from 1.1 through 12.8, giving us a maximum of 96 interrupt sources. Interrupt lines 13, 14, and NMI bypass the Pi block. The interrupt assignment table tells us the location for each interrupt source within the Pi block. Notice the table is numbered from 1.1 through 12.8, perfectly matching the Pi block. The Pi registers consist of 12 Pi interrupt flag registers, 12 Pi interrupt enable registers, a Pi interrupt acknowledge register, and a Pi control register. The enable Pi bit in the Pi control register must be set during initialization for the Pi block to be enabled. The interrupt vector table, as mapped in the Pi interrupt assignment table, is located in the pivect.c file. During initialization in main, we have a function call to picontrol.c. In this file, a memcopy function copies the interrupt vector table to the Pi RAM and then sets enpi to 1, enabling the Pi block. This process is done to set up the vectors for interrupts. In summary, the Pi initialization code flow is as follows. After the device is reset and executes the boot code, the selected boot option determines the code entry point. This figure shows 2 different entry points. The one on the left is for memory block M0 and the one on the right is for flash. In either case, CodeStartBranch.asm has a long branch to the entry point of the runtime support library. After the runtime support library completes execution, it calls main. In main, we have a function call to initialize the interrupt process and enable the Pi block. When an interrupt occurs, the Pi block contains a vector to the interrupt service routine located in default ISR.c. The oscillator PLL clock module has 2 internal 10 MHz oscillators and the availability of an external oscillator or crystal. This provides redundancy in case an oscillator fails, as well as the ability to use multiple oscillators. The asterisks in the multiplexers show the default settings. This module has the capability to clock the watchdog, core, and CPU timer 2 off of independent clock sources if needed. Next, we will look at the details for clocking the core. A clock source can be fed directly into the core or multiplied using the PLL. The PLL gives us the capability to use the internal 10 MHz oscillator, multiply it by 16/2, and run the device at the full 80 MHz clock frequency. If the input clock is removed after the PLL is locked, the input clock fail detect circuitry will issue a limp mode clock of 1 to 4 MHz. Additionally, an internal device reset will be issued. The low-speed peripheral clock prescaler is used to clock some of the communication peripherals. The watchdog timer is a safety feature which resets the device if the program runs away or gets trapped in an unintended infinite loop. The watchdog counter runs independent of the CPU. If the counter overflows, a reset or interrupt is triggered. The CPU must write the correct data key sequence to reset the counter before it overflows. The watchdog must be serviced or disabled within 131,072 watchdog clock cycles after reset. This translates to 13.11 milliseconds with a 10 MHz watchdog clock. The watchdog clock is divided by 512 and pre-scaled if desired. The watchdog disable switch allows the watchdog to be enabled and disabled. The watchdog override switch is a safety mechanism, and once closed, it can only be opened by resetting the device. During initialization, 101 is written into the watchdog check bit fields. Any other values will cause a reset or interrupt. During runtime, the correct keys must be written into the watchdog key register before the watchdog counter overflows and issues a reset or interrupt. Issuing a reset or interrupt is user selectable. Each general purpose I/O pin has a maximum of 4 options, either general purpose I/O or up to 3 possible peripheral pin assignments. This is selected using the GPIO port multiplexer. If the pin is set to GPIO, the direction register sets it as an input or an output. The input qualification will be explained shortly. This figure shows a single GPIO pin. If the pin is set as a GPIO by the GPIO multiplexer, the direction will be set by the GPIO direction register. The GPIO data register will have the value of the pin if set as an input, or write the value of the data register to the pin if set as an output. The data register can be quickly and easily modified using set, clear, or toggle registers. As you can see, the GPIO multiplexer can be set to select up to 3 other possible peripheral pin assignments. Also, the pin has an option for an internal pull-up. The GPIO input qualification feature allows us to filter out noise on a pin. The user would select the number of samples and qualification period. Qualification is available on ports A and B only and is individually selectable per pin. This lab exercise consists of 2 parts. In the first part, we will test the behavior of the watchdog when disabled and enabled. In the second part, we will initialize the peripheral interrupt expansion vectors and use the watchdog to generate an interrupt. You can pause this presentation now and try this exercise on your own, or you can watch me do the lab exercise. A project named Lab 2 has been created for this lab exercise. We will open that project by clicking on Project, Import Existing Project, then we'll navigate to the project, which is Lab 2 Project. Click OK and then Finish. And you'll notice that the project's been added to the Project Explorer window, and here are the files with that project. All the build options have been already configured for this lab exercise. A couple of interesting files we'll take a look at first is the codestartbranch.asm file. Has a user-defined section called code start that's been created, and the code in that section will be longbranch_c_nit00. And if we look at the link a command file, we will notice that there is a section under the sections area, a user-defined section called code start, which is being directed to a memory block called begin_m0, and begin_m0 is located at 0 for a length of 2. longbranch_c_nit00 takes exactly 2 locations in memory. That's why that's set to 2. A couple of things we had to make sure of. We needed to avoid overlaps. So since this block is running a length of 2, the block M0 SARAM starts at 2 now, and we needed to take 2 off its length. The length originally was 400, so now it's going to be 3FE. This avoids an overlap with the next block of memory, which would have been M1. You'll also notice that we are using this R qualifier here. And this qualifier indicates read-only memory, and this is optional. What it does is it causes the linker to flag a warning if any uninitialized sections are linked to this type of memory. So that's a couple of interesting things between code_start_branch.asm and a linker command file. Next file of interest will be the syscontrol.c file. And in here we're taking care of the clocks and the PLL setups. And if you'll notice on the bottom, here are all the clocks enable lines going to the various peripherals on the device. Alright, next file we'll look at will be the watchdog.c file. And in this file here, we're configuring a watchdog. It's been set to be the watchdog disabled and initially set to generate a reset. Another file of interest is the gpio.c file, and this file here we configure all the GPIO pins. As you can see, most of them have been configured for GPIO, except the first one here has been set to EPWM1A. We'll be using that in the next lab exercise. Also on the bottom of this file we have an area for selected pin configurations where we set a couple of pins up. For example, one of them is set up to connect to the LED and blink the LED, and we'll be using that in the next lab exercise as well. So let's take a look and see what's happening here. We'll close out the files that we're not needing right now. And so it's the watchdog one we're going to use first, with the watchdog disabled, generating a reset. So what we'll do is we'll build that right now and check for any problems in the problems window. And then we will click debug. The CCS debug perspective view should open up, which it does, and the program will automatically load and will be at the start of main. So what's happened is after CCS loaded the program, now previously before we clicked the debug, it set the program counter to point to _C_init00. And then from there it ran through the C environment initialization routine in the runtime support library and stopped at the beginning of the main. So CCS did not do a device reset, and as a result the bootloader was bypassed. In the remaining parts of this lab exercise, we will be doing, the device will be going through a series of resets due to the watchdog timer. So what we need to do is we need to configure the device to load the values, and that's with the EMU_key and EMU_B mode, so that the bootloader will jump to memory block M0 SARAM at the location address of 0000. So to set up the EMU key and EMU_B mode, we'll use the script, and we click on script and go down to EMU boot mode select, and we will take EMU boot SARAM. If the device is power cycled between lab exercises or within a lab exercise, be sure to configure the boot mode. In this example here, we're using EMU_boot_SARAM. Okay, now in main, so what we want to do is test out this watchdog. We know it's disabled, and what we'll do is we will go into the loop in the bottom here, and I'm going to right click and I'm going to run to line, and this is equivalent to setting a breakpoint, running to the breakpoint, and removing the breakpoint. So now we're in the main loop. Next thing I'm going to do is I'm going to go to the top part right here and double click here, and what that does is it sets a breakpoint. So what we want to do is test the watchdog out knowing that it's disabled. Alright, what we'll do now is I'm going to run the code for a few seconds and stop the code in a few seconds. So we run and we stop, and you notice it's in the main loop. Once again, run, stop, in the main loop. Okay, this is what should be expected. The watchdog at this point has been disabled, and so we don't expect anything to happen. The breakpoint is being set on the top here to prove that the watchdog is disabled. If the watchdog caused a reset, code execution would have stopped at that point there. So as you can see, we are just still sitting down in that main loop in the bottom. Okay, a couple things. So now we already have the watchdog disabled. Now what we'll do is we will go back to the CCS edit view, and I'm going to open up the watchdog file, which is right here. And what we'll do is we will change the watchdog such that now the watchdog will be enabled. Okay, now the watchdog's enabled, and what we'll do is we'll save that file right there, and we will do a build. And then we will reload the program automatically. And I'm going to switch back to the CCS debug view. And like before, I'm going to come right down to the bottom here and run to line. And as you can see, now we're in the main loop. So the next thing we'll do is we'll run the code. And remember now, this time the watchdog's enabled. So it should generate a reset and get trapped at the breakpoint. So let's try that right now. And sure enough, it does get trapped at the breakpoint. What has happened is as follows. While the code was running, the watchdog timed out and reset the processor. The reset vector was then fetched, and the ROM bootloader began execution. And since the device was in emulation mode, as you might remember, the emulator is connected, the bootloader read the EMU_key and EMU_B mode values from the PI-RAM. Okay, these values were previously set for boot to M0SA RAM boot mode by Code Composer Studio. Since the values did not change and are not affected by reset, the bootloader transferred execution to the beginning of our code, which was at address 0 in memory block M0SA RAM, and the execution continued until the breakpoint was hit in main. And so that's what's happened there. So in the first part, what we've done already is we've had the watchdog disabled, and now the watchdog is being enabled. Okay, now we're going to get to the second part, and we're going to use the watchdog to generate an interrupt. Switching over back to the CCS edit view, a couple of things I'd like you to notice is we have a couple of other files here that we've added to the project, which is called defaultisr.c and the pycontrol.c and pyvec.c, and we'll take a look at these shortly. But what we need to do first in main is we need to uncomment the function call to init pycontrol. And so we're going to do that right now, and I'm going to delete this. So that's the first step. Other thing we need to take a look at, by the way, if you looked at the Pi interrupt assignment table, you'll notice that the watchdog is located in group 1. Pi group number 1, and within that group 8. So it's 1.8. Okay, in main, let's see, a couple of things we need to notice down here. Right here is the code used to enable global interrupts. Right over here. And if we look in our watchdog, we will see code on the bottom here which enables the watchdog in the Pi group. And the next line here enables the core line, interrupt line 1, coming in from that group. So the next thing we'll do is we're going to modify the watchdog to generate, rather than a reset, an interrupt. So I'm going to change that to 2. Okay, and we will save that file off. And what's going to happen is when it generates an interrupt, we will look at defaultisr.c, and there's a section down here, 1.8, which is right here. And that's where our interrupt for our the watchdog will go at the wake int_isr. Here you'll find there's an e-stop instruction. And what this basically does is it's equivalent to putting a breakpoint in the ISR right at this point here. So let's take a look at a couple other files. PyControl.c. That file here is used to initialize the PyRAM. And so you can see on the top here, this section here, the mem copy, is initializing the PyRAM. And I'll show you the PyVec table in a second. And right down on the bottom here, we're enabling the Pi. So when I take a look at the PyVec table, it's this table here that's being copied to the PyRAM. And this matches the Pi assignment table on the slides that you've seen earlier. So that's how the pieces fit together. All right, let's close out these files here. And what I'm going to do is I'm going to rebuild this. And then we're going to load the program automatically. Switch back to CCS debug. Once again, run to line in our main loop. And this time I'm going to run it, and if all goes well, we should have the watchdog generate an interrupt, and we will be trapped in our interrupt service routine, which we are right here at 1.8. So in this lab exercise, we first ran the watchdog disabled, and then we enabled it, and then we changed it from reset over to interrupt and got trapped in an interrupt service routine. I will now terminate the debug session by clicking on the terminate button here. And then we will close down the project by right-clicking and say close project.